الو تيست مايك، الو تيست.
سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم. وعشان بدي المايك لأحمد سامي رئيس قطاع التكنولوجيا. سعداء جدا بوجودكم.
صباح الخير.
بدي المايك
طبعا منورين المكتبة النهاردة. يمكن احنا
صباح
في
الخير.
غاية السعادة النهاردة
طبعا
ان احنا نبدأ
منورين
اليوم بتاع
المكتبة
مكتبة
النهاردة.
الكالكسندريا. يمكن احنا
صباح الخير.
في غاية السعادة النهاردة
طبعا
ان احنا نبدأ
منورين
اليوم
طبعا
مكتبة
النهاردة.
الكالكسندريا.
يمكن
في
صباح الخير.
غاية السعادة النهاردة
طبعا
نبدأ اليوم
طبعا
مكتبة
النهاردة.
الكالكسندريا.
يمكن
في
صباح الخير.
غاية السعادة النهاردة
طبعا
نبدأ اليوم
طبعا
مكتبة الكالكسندريا. طبعا انا برحب
صباح الخير.
غاية السعادة النهاردة نبدأ صديق
طبعا
مكتبة الكالكسندريا. انا برحب غاية السعادة النهاردة نبدأ صديق ان شاء الله مكتبة الكالكسندريا. عليه غاية السعادة النهاردة نبدأ صديق ان شاء الله مكتبة الكالكسندريا. عليه غاية السعادة النهاردة نبدأ صديق ان شاء الله مكتبة الكالكسندريا. عليه غاية السعادة النهاردة نبدأ صديق ان شاء الله مكتبة الكالكسندريا. عليه غاية السعادة النهاردة نبدأ صديق ان شاء الله مكتبة الكالكسندريا. عليه غاية السعادة النهاردة نبدأ صديق ان شاء الله مكتبة الكالكسندريا. عليه غاية السعادة النهاردة نبدأ صديق ان شاء الله مكتبة الكالكسندريا. عليه غاية السعادة النهاردة نبدأ صديق ان شاء الله مكتبة الكالكسندريا. عليه غاية السعادة النهاردة نبدأ صديق ان شاء الله السلام عليكم، انا سعيد جدا ان انا كل سنه موجود النهارده في مكتبه اسكندريه. السلام عليكم، السلام عليكم، انا سعيد جدا ان انا كل سنه موجود النهارده في مكتبه اسكندريه. السلام عليكم، انا سعيد جدا ان انا كل سنه موجود النهارده في مكتبه اسكندريه. سعيد جدا ان انا كل سنه موجود النهارده في مكتبه اسكندريه. دكتور طه سليم، جنرال مانجر وكالة ساس وكو فاوندر اي كافيه وسكيو. اتفضل دكتور طه.
شكرا باشمهندس سامح. Thank you everyone and thanks for this great opportunity and the event. So I'm just preparing my shared screen. Okay, do you see my screen? Okay, yeah, thanks a lot. So welcome everyone, also and welcome to Alexandria Quantum mini-Hackathon and the first Quantum Industry Summit. Indeed, it's a great opportunity, and I really thank Dr. Ahmed Samir and engineer Yusuf Al-Dakar for the great help and the efforts he put in, and also the whole team of Bibliotheca Alexandrina and also the team of the Egyptian quantum community. So this is the first quantum industry summit, and it's a great effort organized by Bibliotheca Alexandrina in collaboration with iQafé and the Egyptian quantum community members. With the powerful capabilities of Bibliotheca Alexandrina and all the army of volunteers, the quantum tech is brought to you at your disposal. And today at Alexandria Quantum mini-Hackathon and also the first Quantum Industry Summit, we are organizing this to keep the powerful momentum initiated at the first Alexandria Quantum Hackathon, which was held in last September last year in 2025. So this is an effort to sustain the ecosystem and also the momentum of the ecosystem and keep the pace with evolving quantum technologies. The event features two interesting activities. The first is a first Quantum Industry Summit. And this brings to you leaders and experts from local and international ecosystem, companies and startups building solutions in or around the quantum technologies in general. So we have Dr. Ahmed Shawqi Moussa from Cairo University and engineer Ahmed Salim from IBM, engineer Sameh Zaghloul from Fixed Solutions, who's also going to be co-chair of the summit today, and engineer Alan Chansey from Molkit SAS. And next to the summit, we have very interesting hackathon. It's a quantum mini-Hackathon, and it features the 5 challenges that we see in the slide. Here we have challenges covering chemistry, like the estimating of the ground state of carbon dioxide using like state-of-the-art algorithms like variational quantum eigensolver and sample-based quantum diagonalization. We have problem related to HP optimization, like optimize the resources and the resource scheduling for compute clusters, and the machine learning problems like ridge regression, linear systems using algorithms like HHL, for example, and also MRI dementia classification. So it's a problem related to healthcare. The fourth problem is about hardware optimization, and this is how to optimize quantum teleportation protocol and optimize a qubit layout to execute this protocol efficiently, taking into account the metrics of the qubit. And this is a first of its kind challenge with respect to the ecosystem in the region about the optimization of hardware, as far as I know, up to my knowledge. And indeed, we have the cybersecurity track, and this is about to design and simulate quantum key distribution system that can involve state-of-the-art and well-known algorithms like BB84 or ECART 91. And together we Summit and the Quantum mini-Hackathon act as a founding pillars and the catalyst for the quantum ecosystem and support the student and the graduates and the whole ecosystem, hopefully, in their journey in quantum tech. So thanks again, and I look forward to seeing you in the event. I would like also to thank the team of our volunteers, also including engineer Mohammed Fergani and Nada Ahmed, and also the rest of the team, Omar Sobhi and Dr. Asma Safan, Ziad Tariq, and many more who helped in behind the scene and also helping today in executing the session, and also the whole army of the mentors who are helping the teams and the whole participants who are taking those challenges and also proceeding with them.
Thank you, Dr. Tom. Now we move to engineer Ahmed Salim.
Assalamu alaikum. Am I audible?
Yes.
Cool. Okay. Sorry, Arabic or English?
English.
Okay. So thank you very much for having me in the mini-Hackathon, and thank you for the Alexandria Bibliotheca for arranging this. It's an honor actually to be for the second time in such a great event to give back to the community and reach the quantum skill sets in the Egyptian market, maybe in the Arab world as well. I'm very passionate about the opportunity, the challenges that we have in this mini hackathons. Very promising. I do expect that a lot of energy will be on this hackathon like the last year. And let me just introduce myself. I'm Ahmed Salim. I'm working like in a superposition in the quantum terms, let's say. So I'm in classical world. I'm working as a technical leader for IBM Saudi Arabia, handling generative AI automation capabilities, helping organizations, government entities here for their transformations. And the other side of the superposition is I'm quantum ambassador. I'm representing IBM in the quantum events, as long as I am a Qiskit advocate as well. So, and I extended the gratitude to all the attendees for giving their time to attend this hackathon and this event. I hope that will be a successful one like the one last year. So I'm super excited about it. I hope you're feeling the same, and thank you for the opportunity.
To the first technical session, Dr. Ahmed Shari Musa, our professor of computational science, about very, very interesting subject as usual, the convergence between HPC and quantum computer.
Thank you, Engineer Sameh. I'm sorry to have to use my sunglasses. I have an eye problem. I will be hardly seeing the slides. So if I talk about something that is not on the screen, just let me know. Okay, before I share, I also wanted to point out, Engineer Sameh, you have a problem with the sound also. It's not clear. I think your mic might have a problem or something. Okay, I will just share the screen itself. And then I can switch easily. Can you all hear me?
Yes.
Okay, good. And now can you see the screen?
Yes.
Okay, great. I'll try to squeeze this as much as I can within the 30 minutes or less because we started late. Okay, the talk is, I'm also like Engineer Ahmed Salim. I'm in the superposition between HPC and the quantum computing. And I'm very interested in this link. It was some sort of fiction until recently. IBM with the University of Riken in Japan joined forces to turn it into a reality rather than being a fiction, trying to make a joint system, which is HPC and the quantum. And we'll see why and how in this talk. So we'll talk about the genesis, the creation, and the prospects, what it might lead to. First, let's have some little talk about HPC. What we see here on the screen is currently the fastest computer in the world. It's called EgQCC. It's in Lawrence Livermore National Laboratory in the United States. And it is an exascale computer. Exa means 18 zeros. So it is a number multiplied by million, trillion operations every second. And down here are the basic specs of the computer. You can see the basic and the detailed specs on top500.org. You just go on Google and write top500.org, and you can see everything. But what is amazing is, of course, this is one of currently only 4 computers in the world who are in the exa scale, capable of doing millions of trillions of operations every second. Of course, this huge speed in computation not only affected computation, but it affected all types of science and engineering, because with these speeds, we are able to simulate processes and systems that we were not able to simulate before. And this transformed the science. In the old days, the science used to be theoretical or experimental. Unfortunately, those days are gone. We don't have something in the science that I am aware of that can be abstracted or modeled in a single or a couple of equations anymore. So these days are gone. On the other hand, we started facing some difficulties, not difficulties, actually impossibilities in running certain experiments. And we will see why in a few minutes. So some problems in the science cannot be dealt with, cannot be modeled in an equation or two, and cannot be played with in physical experiments. So what do we do? This is what the high speeds of high performance computing enabled us, is to practice science computationally. So now, instead of being a theoretical physicist or an experimental biologist, now we can be computational scientist or computational chemist, computational biophysicist, because you practice the science computationally and you bring the results. Later on, actually, recently, this became even more difficult when we don't have a theoretical model, we are not able to run an experiment, and we do not even have a computational model to run. And in this case, we are stuck with what we call data-driven science. So it's science about something that all we have for is data. Of course, data is huge, it's big data, with all its varieties of variations of being big, like the veracity, the volume, and all these things. And we don't have a computational model, so we have to deal with this data to extract and to generate science. So these are the modern practices of science due to the advances in high performance computing. So now we are able to do that. Instead of experimentally, we do it in large scale simulations that require huge speeds. Examples of this is what we see here. We used to need wind tunnels to design and manufacture airplanes or cars or things like that. So we utilize everything we know about the mechanics and material science and everything, and we make the design. We build the system, and then in the old days, we used to take that model or maquette that we developed and go to a wind tunnel, large wind tunnel, big enough to host a whole airplane, as we can see, or a whole truck like that, and generate the winds, because we want to test things on that system or on that airplane or on that vehicle in different weather conditions. And we cannot wait until the required weather conditions occur, because they might never occur. But if they occur after we deploy the system, it could be a disaster. So we generate the winds in the intensity we need, in the directions we need. We generate everything, and we see if it affects the tail of the plane or the wing or the body or something. If the test fails, we cannot do anything other than rebuilding the whole airplane or the whole car and redoing this again. This used to take years and huge amounts of money. Now we can simulate this process. We can simulate everything, including the wind tunnel simulation. And it reached actually a level of accuracy that when we run the physical test at the end, we need to run it only once in most cases. So it became really very accurate. Same thing for designing and building the airplane itself. we build it with simulators. We simulate everything with large-scale simulators. You can see here, this is a whole room. This is the car, and these are 3 people here. So you can see how costly and how difficult it is to build this wind tunnel. We still have them because we still need to use them, but instead of using them repeatedly and rebuilding the plane itself repeatedly, now we reach the level of accuracy where we can just make the final test in the wind tunnel only once, and that's it. And that reduced the time for coming up with a plane from just an idea until it is deployed in the market. In the old days, it used to take 15, 20 years. Now sometimes it takes only 3 years. You can see the effect. Some other cases where we have like astrophysics. You want to study something that you have a model for, but you cannot run an experiment to see how a galaxy will evolve or a climate evolution will happen in hundreds of thousands of years, but you can simulate that, and you come up with the simulation results. And as I said, also, it became very accurate. Another field is nuclear energy. You can simulate the whole system, simulate everything. You don't need to do like Oppenheimer did in the famous movie and run away to hide behind the mountain to see what the explosion will do. You can do everything with simulation. Also, down there is the stem cell research and other biological research where you can simulate the whole biological system with all accuracy, levels of accuracy of details, and you come up with the results that are needed for diagnosis, drug design, treatment plans, and everything. Of course, this is a huge economic impact. As you can see, like we said, like in the airplane, maybe we don't try to simulate a crash test in airplanes because we know that plane crashing are disastrous anyway. But for cars, we want the cars to be able to stand some certain level of crashes. So in the old days, they used to also, as I said, build a car and then build a cement wall and run the car at, for example, 100 kilometers per hour and get the car to crash into that wall and see what happens to the car and to the passenger, which is, of course, in this case, replaced by a dummy. Nowadays, as you can see, car manufacturers save 100 million. Sorry, this is for the airplanes just to simulate the logistics. But with cars, you can save $1 billion per company per year for crash testing only, other than the other tests. This is for weather simulation to avoid the problems. For the biology-oriented or biology major people, when we are talking about drug design in the modern era, we try to design drugs that attack certain molecules. So to attack this certain molecules and treat it or destroy it or do something to it, we have to know in detail the structure of that protein. After we know the structure of the protein, this is not enough. We need to see how this protein folds and unfolds in response to drugs. With the high-performance computing systems on the petascale, which is not million trillion operations per second like El Capitan, but on 1,000 trillion operations per second, you need one of these computers to run for a whole year to simulate the protein folding, a protein that is not that big. It's, as you can see, only 300 amino acids. You want to simulate the folding and the unfolding for only 1 millisecond. You need a petaflop computer to run for a whole year. Now, what if we need to simulate 1 second? Then you must multiply something by 1,000. Either multiply the computer by 1,000 or multiply the time by 1,000 to run for 1,000 years rather than 1 year. Now, to understand this problem, a miniature part of this problem is given to, we can say that this computer is a dream computer to anyone who has a laptop. So if you have a laptop that has 3090, RTX 3090 or A100, that would be really a dream laptop. Very few people in the world have something like this. To use that for this kind of simulation, it would take nearly 55 years. Now you upgrade to higher GPUs and you reduce that to 5.5. And nowadays, with certain supercomputers, you can finish this in 10 days. And if you finish it in 10 days, then the rest of the time is given to drug design, drug trials, and all these things. The fields are unlimited. It's from car design to coffees to tissues and paper towels manufacturing. All these are material science. But not only that, but also the entertainment industry. This is, I would say, very quickly, we had a movie called Shrek, which started the first one in 2000. And I think the last one, I don't know if they made another one or not, but the last one I know of was 2010. This one, to render the animation, it utilized 50 million core hours. What does that mean? It means that if we are using only one core, which is the top of the line, like the fastest processor in the world, but it's only one processor running this rendering, it would have taken 50 million hours. If you want to verify what I will say now, verify it on a calculator. 50 million hours is approximately 5,800 years to do this. With HPC, we were able to render it and make the movie and show it in the movie theater. This, of course, led to the big integration between different types of sciences. Like, for example, in the old days, computing people used to look for Turing Award. But physics, chemistry, and biology people used to look for Nobel Prizes because Nobel is available for these fields. It's not available for computing. But surprisingly, in 2024, the winners of Nobel Prize were actually computing and AI scientists, and this was due to their contribution in revealing new science in physics and chemistry using AI and computing techniques. Okay, since we are able to like simulate all these things now, let's take a specific equation in a specific subject in physics that we want to simulate. Can we simulate something that has to do with quantum, not computing, but quantum technology, quantum physics? Can we make benefit? Can we use the HPC systems to simulate that and come up with the result? The answer is yes. Let's take a very basic fundamental example, which is Schrödinger equation, which is a complex function of energy and psi. This is the origin of the discrete energy levels in quantum mechanics, which was used after that also in quantum computing. I think some of you who are physicists definitely understand the equation and how it is built. As I said, an equation like that is considered simple with nowadays modern science, and we don't have equations that simple anymore. But even though, let's take this example to see what we can do with. So now we want to calculate, this is the general solution for the wave function and energy levels. I'll try to skip over the derivation. It's not that necessary. So this is the general solution. And it can be verified by substitution. See that now the energy equals this by substitution of the psi. Now, the general solution is a plane wave function. So this is the wave vector. And as we can see, E, the wave, I'm sorry, the solution is available for all Ks. All Ks, it's not discrete. We can substitute for K and get a solution for any K, but this is not the reality, because doing this means that E is not quantized, and we want E to be quantized. So can we do something about that using classical computers and HPC? Yes. We went to the probability of finding a particle in a region. This is the equation. We want to do the integration to the integral of psi dx to try to quantize, make it in a limited space. And now A must be infinitely small. And until now, we don't have that. So let's try to fix it. We went through some derivation. We enhanced the model gradually. This is the mathematical. So usually people ask for English. Please, what does that mean in English terms? So these are the equations. And now we have standing waves like a vibrating strings. So even though it is like a quantum physics equation, but we have something similar to the standing wave of strings. Since Schrödinger equation is a linear equation, some of the solutions here are also possible, and these are the standing waves that we came up with. So at the end, we were able to quantify this, to make it quantized, to make it in certain levels and not other levels. So this is what we are able to do. So we are able to actually run quantum physics simulations on an HPC. Unfortunately, it takes huge time to do this, and it requires computers that are even much more powerful than the EgQCC, which is the top of the line in the world right now. And it takes years and billions or trillions of dollars to generate a faster one. So what is a promising field to do this? When we came up with the quantum computers, which are this is the basis of classical computing. Everything is in zeros and ones. So the instructions that we write in a language that we see as similar to English, at the end of the computer sees it like a bunch of zeros and ones like this, and they are deterministic zeros and ones. Quantum computers came up with a problem and an advantage. The problem is we have actually many problems: coherence, error correction, uncertainty, lots of things. But if we are able to deal with that, then with every single qubit, we have pretty much infinite number of possibilities due to the superposition characteristic of the quantum bits. So the bit is not limited to 0 or 1, it is 0 and 1 and any coefficient in between. Unfortunately, this is the main limitation. We cannot measure the coefficient in the middle of the calculation. We have to wait until the end, and then we measure it to translate it into 0 with a coefficient and 1 with a coefficient. If we measure it in the middle, it is destroyed, and we cannot use it anymore. So unlike classical computing, which is reversible operations, we can stop in the middle at any time, go 1 step, 2 steps, or go all the way back and then restart the computation. With quantum computing, we cannot do this. However, the big advantage is that all these possible states in the middle between zeros and 1 are used in computation simultaneously. So we have a type of parallelism on the single bit, or let's say single qubit level. So this is the big advantage, and this is why it gives us, instead of possibilities zeros and ones, 0 and 1 for each bit, it gives us the possibility of combinations of zeros and ones for combination of bits. We don't have to size by adding bits singularly, like 1 bit at a time. So here appears the real advantage. When you go to 300, for example, qubits, it is the equivalent of 2 to the 300 bits. You can see the difference is huge now. So if we only go to 13 qubits here, this is the equivalent of 1 kilobyte of classical bits. A big advantage, but as I said, it comes at a price. So people expect that this advantage is going to make quantum computers the next generation or a superset of HPCs. Actually, this is not true. HPCs will still have their advantages, and quantum computer will have their advantage. Or for example, now if we want to prove or simulate or actually run a system, a quantum mechanical system of Schrodinger equation, in this case, we don't need to simulate it, but we can actually run it on a quantum computer directly. So it is the right connection between the computer and the simulated system. Of course, it will run much faster and more accurate and more realistically. Some other very promising fields, for example, are the cryptography. Current classical computers like EgQCC, I think it will take a couple of tens of millions of years or hundreds of millions of years to break the current top-of-the-art cryptographic system using classical computers. But it is expected that with quantum computers having the advantage of every single qubit running multiple states will mean that we will be able to break. Until a few months ago, they used to say between few days and maybe a week or so. I think the last reports are talking about real-time decryption of the whole system. This is, of course, very dangerous, very impactful to have all the systems, military, financial, health system, everything broken instantaneously if you have the required or the necessary computer. So if we want to compare them, it is not actually a comparison of which is better. Quantum computer is not the next step. It is not a superset of, it's not superior to HPC. It will excel over HPC in certain applications, but HPC will excel on other applications. Plus, we will continue to need classical computers as long as we are not able to build quantum phones, quantum laptops, or quantum watches, things that we are using now. These are not going to be available in quantum technology very soon. Okay, that means that somebody must be still working on the HPC systems to make them even faster, because it looks like we will continue to need them. They will not be replaced by the quantum computers. This is actually happening in about 4 or 5 countries in the world right now. One of them is Japan, and Japan is working actually in 2 directions. They are working on HPC. They are trying now to reach the zeta scale. Zeta scale is 1,000 exa, which means they want to build a computer capable of running billion, trillion operations every second. And by the way, they're not just trying, they're close. They're about to reveal it shortly. On the other hand, these are computers that became available in the market. Some of them are good for only good for education, but they are available in the market. But going back to Japan, Japan is cooperating now with IBM to build, this is the genesis that I was talking about, to build a hybrid quantum HPC system. So this is what they are trying to do now, and they actually made huge leaps, big successes. So the University of Riken, which used to cooperate with Fujitsu to build the fastest computers in the world at certain times. Now they are cooperating with IBM to build a hybrid quantum classical HPC system. This is happening actually. It is on trial. Programs are running, and the integration is now on the programming language level. So that now you should be able soon to write a program that is able to distribute the computation not only between different cores and different nodes, but actually between different classical and quantum components on the same system. So in conclusion, we need to understand that HPCs and quantum computers are not rivals. They are not competitors. They are different directions to lead to joint objectives. So they destined to coexist together. They are destined to cooperate together, not only as HPC and the quantum, but actually as HPC quantum or quantum HPC. And I expect that things like that will be revealed. They are already revealed, as I told you about the project of IBM and RIKEN. But news about this are going to be revealed continuously in the next few, I would not say years, but actually months, and continue. We will see how they evolve. Finally, the theory of computation are different, completely different between HPC or classical computing and quantum computing. But the theory of computability still remains the same. What is computable on quantum computer will be computable on HPC, and what is computable in HPC will be computable on quantum computers. But of course, with different speeds, with different advantages. But if something is not made for a computer, the quantum computer is not going to handle this. It will still be a computer. This ends my talk. I don't remember when I started. I hope I didn't use more than the 30 minutes. And this concludes my talk. If you have any questions or any discussions, here is my email. I will be happy to hear from any of you.
Thank you very much, Dr. Schmidt. So from hardware
Engineer Sameh, the sound on your side is still not good. Is there any way?
actually, can you check Ahmed, can you hear me?
I don't know what you said, but I think you asked if it is better, but it is not. It is the same. I'm not hearing anything now. I don't know if am I the only one who cannot hear anything?
No, the same here also. Maybe the noise cancelling is playing some role also in chopping sound.
Okay.
Then if so, maybe we can cancel the noise cancelling from Zoom and also from the laptop itself if it is Mac OS or so, and then hopefully it will not chop the echo.
Mhm. Mm. Dr. Tay, can you hear me now?
Yes, we can hear you. I think yeah, there is a bit of
Okay, great. Okay. Now from hardware part presented by Dr. Ahmed Shawi. It was a software part actually will be presented by Engineer Hassan, IBM Quantum ambassador, developing innovation in software, the hardware aspect part in quantum computer.
The sound is distorted, Engineer Sameh, very much distorted.
yes.
Could be the mic or something to if you can replace the mic or use the internal mic of the computer you're using.
Ahmed Salim, can you hear me, right? Okay. The
I
problem
hear you,
is,
but the sound is distorted.
yes, we are trying to fix this problem. But meanwhile, actually, we'll start, Ahmed Salim will start the software part actually for quantum computing and hardware generation. Please go on, Ahmed.
Okay, so thank you very much. I will share my screen. Okay, can you see my screen?
Yes.
Okay, what about the sound? Is it good, audible?
Yeah, it's very good.
Okay, great. Okay, thank you very much, Dr. Ahmed Shawqi. Definitely, I enjoyed the presentation as usual. You paved the way for me and make my my mission easier. You just explained the basics of quantum computing and the relation between the HPC and the quantum machine, which is really inspiring. So let's get started. So I will try to have it in a brief because I think we are in a shortened time, but let me highlight some stuff related to the software innovation journey when it comes into the quantum computing and the relation between the quantum computers and the HPCs. So let's get started. We'll start with the mission of IBM. The mission of IBM, it has two main points, two main goals. The first one is bringing the quantum, useful quantum to the world so we can get benefits out of our life. And the second one, I make the world quantum safe. And I think the second part, inshallah, will be handled by Engineer Sameh Zaghloul in one of his amazing presentation about quantum cryptography. So these are the two main themes, let's say, that IBM is focusing on. And this is like one um, picture about IBM Quantum. So when it comes into bringing a quantum useful to the community and to the world, definitely we need two main things. First one is a platform where we can solve our problems and how we can do this. This is like a traditional jobs, the day-to-day that we have. You need to build an application. So what you need a laptop, right? And a programming language, one of the programming languages that you have, maybe in this era we have vibe coding and all this stuff. We'll not go on these complications, but let's make it simple. So you need a platform to build and test your applications, model your application, and a programming language will help you to do this. So when it comes into the platform, IBM revealed its first cloud quantum computer on the cloud in 2016, and it was available and is still available for anyone who can log in, create a user on quantum.ibm.com, and he can access real quantum hardware. He can play with some qubits, maybe 3 or 5, from 3 to 5 qubits, as far as I remember. Starting from this, we start building the ecosystem around the quantum, helping the community. When it comes into the coming slide, we'll highlight this one. And the second part is the tool, which is what we call it a casket. Casket is an SDK. It's provide a flexible way for the developers, scientists, researchers to map their real life problem and model it and encapsulate this information into a quantum way that it can be deployed on quantum machine and seeking reaching resolutions, simulation optimization, different types of problems that we have as we speak. So the casket, as I mentioned, it's a SDK, and IBM, when it comes into building the ecosystem, they try to find an easy programming language, popular programming language, easy to use. Most of developers worldwide using it to make it simple. And instead of inventing a new programming language to use it to program your problems on a quantum machine, so they selected Python, well known, very popular, easy to learn, and we built the casket on top of it. Okay, and this picture, it showed you the multiple stacks of caskets that we can touch the base in the coming slides. But when it comes into building a useful quantum computers, it should be definitely integrated with our other capabilities that we have, and we have invested definitely, like what Dr. Ahmed highlighted, the HPC. We spend billions and billions of dollars building these massive machines, but we need to capitalize on this investment. I will not say, okay, I have a quantum machine, keep the HPC aside, and I'm fully biased to the quantum, so let's make all the problems, solve it on a quantum fashion. This is not the case, because we need to get the benefits out of the ecosystem and what are the scientific breakthrough that the humanity did in the last decades, and make it hand in hand work with the quantum in a one system in a very orchestrated way. So we focus on managing the quantum, building the quantum industry. At the same time, integrate partnership with the existing technologies, communities that make advantages, and make it work hand in hand like one system to be able to resolve the complications and the problems that it's not being solved till the moment. From here, I want to show you, this is the IBM roadmap for the quantum-centric supercomputing. As I mentioned, we started in 2016, and since then till 2025, last year, we never missed single milestone. As you can see, we have many milestones on different levels. If you will look it into from bottom up, you have the hardware layer. This is the black gray area. Okay, where we have all the invention when it comes into the hardware and building the quantum processors. Then moving up on the building the algorithms, the languages, the programming languages that we will use to model our problems, and going up to a more abstraction layer to make it easy to developers, researchers, scientists to model their problems, their simulation problems, optimization problems, without caring more about the underlying hardware and the architecture of the processor, like the way that we are building our programs as we speak. Okay, and I mean in the classical way. So to have this quantum-centric supercomputing, definitely we need to focus on the modularity for the quantum, so I can have multiple modules working together as one system. The communication for quantum, if I have multiple quantum machines, or even HPC plus quantum machines, how I can do the communication between these two different worlds, let's say. And definitely the need of the middleware layer for the quantum machine, to be specific, and definitely extend this middleware layer to have an orchestration between the quantum and the HPCs, which is working in the classical fashion. So out of this roadmap, as you can see, it's a very promising one. It's covering 2033 and beyond. Definitely in 2026, this is the year that we are on, and we didn't announce about the discoveries and all the achievements that we did to match this roadmap. Usually it will be end of the year, October, November, something like that. So out of this holistic view of the IBM roadmap, let's focus on this small part, which is related to the blue part, which is related to the software. Okay, this is the software layer on top of the quantum processors. As you can see, we had many milestones. The last one is the building an API with C languages, where we can facilitate the way or pave the way to communicate with the HPCs, like what we will see on the coming slides. So to do some projection of what Dr. Ahmed mentioned, that it's not only quantum or HPC, it's both together, both world together, quantum and the classical. We need to get the maximum, the advantage of the quantum machine for parallel processing and the massive power and the throughput of the HPCs. Okay, so this is a picture showed you how this communication is being done. So we have here the quantum systems here can communicate with the CPU and GPU, which is what we call it a traditional computing fashion of machines. So we have these both working hand in hand. Definitely, there is a lot of layers, like what I mentioned in the past slide. We have many challenges in the communication between the classical and quantum. If they are embedded in one system, close together, or maybe distance, there is distance between the quantum systems and the HPCs. So these a lot of scientific discoveries that IBM even published papers how they do innovation in the communication part, and we had the partnerships with Cisco, with AMD, and many market players that can partner with IBM to build a useful quantum ecosystem, as I mentioned. We have, for example, the L couplers, which is a special type of connectivity to connect different quantum systems to work as a one cluster. So this is when it comes into the systems on high level, but how we can do this? Definitely we need a tool or a programming language that can enable us to do this synergy between the HPC and the quantum machines. And as I mentioned, Cascade built on top of Python. And recently IBM revamped the core or back-end system of the Cascade to be on Rust. And in the coming slide, I'll tell you why we moved to Rust as a backend. But this gives us a flexibility. One of the advantages that us the flexibility to build a C APIs like an interfaces and make it easy to scientists and researchers to model and develop their algorithms and run it side by side with HPC and the quantum machines. So we have, as you can see in this picture, we have two modes: the standalone build for Qiskit, which has the Rust as a backend, but there is no link between Rust and the Python interface. And we have on the second mode the embedded Python extension. So you have a link between the Rust as a backend and the C program, where you can make it like an interface to your HPC computer and start working in a harmony between the quantum machines and the HPCs. So in this slide, I'll tell you why IBM moved to Rust, which is a very key move, and we say it a breakthrough when it comes into running on the quantum and the HPC on the same context and resolving the same issue. We found out that Python has problems when it comes into the parallel compiling time, the running on the concurrency issue, and we found out Rust is excel in this part, which allow IBM to seamlessly write multi-threaded code without any issue. Okay. The second reason why we use Rust or build Rust, we have the Python-centric data model. It's a and the pure Rust implementation allow IBM to introduce the C level, because the interface, exposing the interface from Python to C, it has many complications, and we found out Rust will make it easier to build the C APIs and make it easier for the researchers to integrate and build their problems on top of it. So, and the last, by the way, the last advantage of having Rust, and this is what IBM emphasized on, it will keep enhancing in the underlying layer or the backend of Rust, this layer, where the end user or the developer or the scientist will make a huge improvement when it comes in running their job. So it will run faster. And the code change at the Python layer or the upper layer, it will be very, very, very minimal. So there is no paradigm shift, let's say, in the programming style, or even you want to start learn Rust as well. Okay, so if you know Rust, you can expose the APIs and you can work with it. If you are continuous Python, you find it a good yani programming buddy for you and you're familiar with, you can continue with it. But the change or the enhancement in the Rust or the backend layer definitely give a huge advantage in running the jobs on the IBM Quantum processors, and the minimal impact in the developer or the scientist to model their problems. So when we think in the foundation of designing and building the algorithms, that definitely you will use it during this hackathon, we have two ways. We must continue to find a seamless way to integrate the quantum and the scientific computing environment, because researchers and scientists, they have their own tools, right? They are working their own tools away from the quantum computing. So how we can save this effort? They did this investment, time and effort in developing and using some external tools, and how we can get benefits and make it a seamless to the scientist and get benefits and run their algorithms on the quantum machine. So this is the first pillar that we will focus on. And the second one, to develop new capabilities for the quantum-centric supercomputers to enable more efficient algorithms. So working the quantum and the HPC hand in hand definitely will enable us to explore new algorithms solving problems that will never be solvable by quantum machines alone or the HPCs alone. And if you can see for the left side, this graph, the purple boxes, you can see it is representing the quantum part, and maybe the dark and the gray, it's representing the classical part. So we have this orchestration layer to make it work both as an one system. When it comes into the second pillar, to develop the capabilities, these are the main steps that we are following when it comes into modeling the problems and running in a quantum machine. So you start, any scientist or the developer start mapping the problems into a circuit. Then Qiskit will start optimizing this algorithm to fit with the backend hardware. Then the execution layer, where we'll start executing this circuit against quantum hardware. And the post-processing, you might have some of the post-processing to be done on HPC or any classical machine. So this is the high level theme and the way that we can interact between these two worlds. So let's deep a little bit deeper, so we understand that, okay, we have quantum, it has its own libraries, it has its own tools, and we have the HPCs, even it has its own tools as well. So as I mentioned, IBM working hand in hand with the community, with the ecosystem, a huge contributor in the quantum resource management interface. This is a new open source library. It's a vendor neutral library that it can be used by any quantum machine with any other architecture. And this is like a thin layer that it can interact between or manage the work between the quantum machines and the HPC. And we know Slurm, it's the job scheduler used, and it's a familiar term for the HPC people. However, we need to have the quantum version of it, let's say. So this is what IBM, with all these list of contributors, to build this open libraries to be able to run and give a seamless experience to the scientists and model their problems in an efficient way. You might have some familiar names like Cleveland Clinic, Oak Ridge National Laboratory, Ministry of Energy in US, and more. And even in the hardware supported, we are supporting IBM. We are relying on the superconducting when it comes into building our processors, and we have Pascal, which is using a different quantum architecture to build their machines. And this is the ultimate goal. We partner with the community to bring a useful quantum machine to the world. This is one of the success stories that we did with the RPI. It's an institute in New York. We run a quantum system 2, which has Eagle processor. It's 127 qubit, and it runs with the AIMOS supercomputer. It's 10 miles away. As I mentioned before, the communications we are building currently are innovating new way of communications between quantum and HPCs to be able to work as one system at a distance. And this is one of the use cases and success stories that we have in place. I have something visual for you to show you how the orchestration between the classical and the quantum machine is working. Let's start from the beginning. As you can see here, these are the resource information. This is the backend where I will run the algorithm. Then they will submit. This is the submission file. This is the job file that it will run with the HPC, and it is creating the workflow as you can see on the screen, and there is the Slurm queue to start executing the job. Now we are checking the logs, and the workflow files has the results in the JSON format, and you can see the SQD results. This is one of the algorithms that use the HPC and the quantum machine, and I think you might use it in one of your problems, solving your problems. So this is on high level how we can do this synergy and the parallel work between the HPC and the quantum machines. At the same time, make it easier to the scientists and the learners, technical team, or even researchers, scientists to model their problems without worrying about the underlying orchestration. Okay. One thing that I want to highlight, it might be a good benefit for many of you, which is the cascade functions overview. The cascade function, this is the full stack of the cascade, how it works, and what are the different layers that we are using cascade. The blue or the lower part is the hardware part, the quantum computer. And as you can see, the small one is the quantum chip. It's part of the quantum processing unit because this might be one chip or more than chip. And the cascade runtime services, which is translate your algorithm and make it like circuit friendly, let's say, or quantum processor friendly, because it knows the architecture, the healthy qubits, the coherence type of each and every one. There are a lot of magic happening here to give you a proper and the most efficient runtime. And you have side by side is the HPCs, which it might be a CPU, GPU, or AIU. AIU, it's one of the AI chips that IBM built, running on their mainframes. And on top of this, the Cascade serverless. This is the orchestration layer, as I mentioned, between the quantum and the HPC. And on top of it, there are two very important functions, circuit functions and application functions. Circuit functions, this is to improve the result or the quality for your algorithms, and this is including the error suppression and error mitigation workflows. So you are developing on functions on a circuit level, or a different type of functions is application layer, where it's a reusable component pre-built maybe by partners, and industry experts to make your life easier, modeling or enhancing your problem modeling, and definitely it will save you maybe time, effort, cost when running your algorithm on real quantum hardware. There is a note that the premium and the flex users can explore free trials of this. These are paid functions, and why I'm highlighting this, because you might build your own application function and you can contact IBM to host your function on IBM marketplace, so you can monetize your work. Okay. And these are examples of the current application functions and circuit functions. We have many partners in our ecosystem, so we are developing many functions as you just mentioned. As mentioned here, we have 6 applications and the 3 circuit functions. The eligible program, this is for customers who has a subscription with IBM. Sorry, is there any problem in seeing my slides?
No, they are visible.
Sorry?
They are visible.
Okay, so we are good. Okay, cool. So after having this overview on the casket, we have the casket performance, and we need to measure the casket against all the SDKs and the tools that we have in the market, and that's why IBM created bench press. This is a huge list of tests, more than 1,000 tests, to verify all the tools that dealing with the quantum machines, so we can see which one is efficient in the performance, maybe in accuracy, which one failed on the tests, which passed, and so on and so forth. Because from time to time you can find a lot of claims in the market. Okay, we have the best toolkit, we have the best quantum machine, we have the best and best and best, and this definitely with each and every sorry, with each and every publication, everyone in the market wants to verify this. So IBM think to have a GitHub published to the public. You can access it and see the results of these different tools against the defined tests. Okay, and we have as well the Rust works. This is the library for Rust. You can use it to develop your algorithms. So IBM tried to unify the efforts and make one measure for all the advancement that we are doing in the market, either IBM or non-IBM vendor, which are the quantum players in the market. In a couple of slides, I show you the difference in when it comes into the performance between IBM Qiskit and TKIT. This is one of the tools in the quantum, and you can see huge difference in the running time. Some of the takes 5 minutes comparing to 27 hours, which is a huge difference when it comes into the performance. And by the way, the reference are mentioned in the slide where you can verify these numbers. And as you can see, we have a small table to where we shortlist the best kits in the market. As you can see, Qiskit is the only SDK that never failed in a single test. Others, they failed, and as you have here these statistics to give you a glance how we are building a solid foundation for the quantum industry, and we are keep innovating on this area. By the way, not only IBM, we are not claiming that it's an open source, and the contribution with the community really adds a lot of innovation to the project. I'm about to finish. I think I have like 1 minute and a half. So the Qiskit education, from where you can learn Qiskit. We have online Qiskit classroom modules It will give you a glance about the basics of the Qiskit, and we have classroom 1 to 2 hours long, I think, of Jupyter notebooks on key quantum computing concepts. We have a quantum learning portal. It's open for anyone, and it has different levels from foundation to focused and advanced topics, from beginners to experts, so who can handle this. And this is why IBM working with the community. We have a quantum learning, as I mentioned. We have the Qiskit. IBM is doing a yearly Qiskit Global Summer School. We have Qiskit YouTube channel. I highly recommend to subscribe to it to be on top of the latest innovation and the discoveries from IBM. We have Qiskit developer certification. We have a set of certifications you can study and be Qiskit certified, Qiskit advocates, leverage your experience in this domain. And the Quantum Developer Conference, we are doing this in yearly basis to announce about our innovation and the latest discovery that we achieved in the quantum era. By this slide, I will finish my presentation. Thank you for your time and listening. I think I'm on time, and if you have any question, you are welcome.
Thank you very much, Ahmed.
Sure.
By the way, can you hear me?
Yes, I can hear you. Thank you.
Okay, so problem fixed. Now actually from hardware and software.
Now the voice is much better. Thank you.
Now from hardware part and software part, how to merge actually this with Alan Jansay, president of EgQCC, with a real use case actually for the innovation part, how to create algorithm that has real business useful case scenario. Alan, floor is yours.
Hello, thank you for having me. Hopefully you can see my screen. Can you confirm you can see my screen? I'm sharing my screen.
Not yet.
Yes, we can see it.
Yeah, but okay, this is the presentation. So can you confirm you can see my presentation, please?
Yes.
Hello, can you confirm?
Yes.
Yeah. Thank you for having me again. So today it's a different topic. It's not sample-based quantum diagonalization. I'm going to share with you work we did with the quantum with Professor Marcel Merck and his team from NICF Institute and Maastricht University in the Netherlands. And it's about a toy model for reconstructing particle tracks at the LHCb at CERN, which is I will explain. So let's move on. Sorry. See if I can move to the next slide. Doesn't seem to move. So we share again. Okay, let me share again. Okay. Sorry, so hopefully you can see what I'm sharing. Can you please confirm? You can see? Okay,
yes, we can see.
So introducing myself briefly. For more details, please have a look at my LinkedIn profile. I'm the president and co-founder of EgQCC. The other co-founder is Dr. Taha Selim. And EgQCC is a startup, already a member of QEDC and Quick. I was invited twice by IBM to attend their IBM Quantum Developer Conference. The first one was in Poughkeepsie, state of New York. The second one in Atlanta. And last time I was part of a team who won the market split problem coding challenge. So great to be among the top developers. My expertise: quantum computing, quantum algorithms, quantum optimization, quantum chemistry, I would add that at the beginning of my career, I spent a number of years with Cray Research. Cray now part of HPE, and of course it's about HPC. So I've been involved in the distributed HPC and later quantum for a number of years. 3 publications you can see on the right-hand side: Quantum Chemistry and Computing for the Curious. I'm the co-author. I have focused my collaboration on developing code in Python, and of course Qiskit, and Dr. Kipper Sharkey is one of the leading quantum chemistry experts. And my qualification, I'm not an academic. I've got a degree from École des Mines in Saint-Étienne, which is executive engineering in France. So having said that, I move on to the next slide. I hope. Can you confirm you can see the next slide, which is an abstract of what I'm going to talk about? Yes.
Yeah.
Great. So as I said, it's a toy model, and it's based on the following work. So I'll give the reference. On the left-hand side, you see a picture part of the LHCb and the detector we're going to talk about. So this is the agenda. Only have half an hour, so we'll move pretty fast. So what's the Large Hadron Collider Beauty? What's a beautiful name, right? LHCb.
Could you please run it in the presentation mode?
No, because then it doesn't move from one slide to another, unfortunately. This is what
Okay.
I tried earlier on, and for some reason it gets stuck. It doesn't move from one slide to the next one. So that's why yeah, that's unfortunate, but that's the way it is. So so the LHCb experiment at CERN is a general purpose detector. There are 4 general purpose detectors at CERN, and there is the Atlas CMS, and there is the LHCb, which initially was specialized in investigating the slight differences between matter and antimatter by studying a type of particle called the beauty quark, or B like bottom quark, but beauty, so much beautiful. And quarks are components of many particles, including the protons, neutrons. So the LHCb uses a series of subdetectors to detect mainly forward particles, those which are thrown forwards by the collision in one direction. So the first subdetector is mounted close to the collision point, with the others following one behind the other over a length of about 20 meters. To give you an idea, it's very heavy, 5,600 tons, and it's 21 meters long, 10 meters high, and 13 meters wide, and it sits 100 meters below ground near the town of Ferney-Voltaire, France. But actually, the LHC collider runs across France and Switzerland, and you can actually visit at CERN, and when the colliders are not operating, you can actually go down and have a peek at the actual detectors. What is very impressive is the number of people. More than 1,600 members from 98 institutes in 22 countries, including 1,100 authors. They collaborate to this experiment. It's a huge international research endeavor. Okay, so this is gives you an idea. So it's actually produced by one of the programs I share on GitHub. So you see on the left-hand side there is you actually don't see the so-called primary vertex where the collision occurs in the first place, but you see at the beginning from left to right the traces in red are fairly dense, and then they separate. And the trick is to reconstruct what is shown here in blue lines, which is the tracks of the particles. And once you have got the tracks of the particles, it's easy to by intersection, by geometry in 3D, to work out the collision point, which is called the primary vertex. And it happens that the subdetector, which is closest to the collision point, it contains a negligible magnetic field, which means it's not bent like you would see collision tracks in other experiments like the Atlas or CMX experiment. So that makes it a bit easier, right? So, but what's the connection, you might ask, to quantum computing? So the team of Professor Marcel Merck, Maastricht University, they have worked out original approach. They built a Hamiltonian. So this is the way it is built. The only important caveat is that in order to construct the Hamiltonian, somehow you must have more or less solved the problem in the first place classically. So this is why it's called a toy model, because the ambition is not to produce a solution that could be actually put into production, but to illustrate what can be done. But for now, as input to the what will follow the quantum computing part, it's actually built well from it's generated by a dedicated program. And so let's move on. So it is cleverly transformed into a so-called Ising-like Hamiltonian, and it is solved using matrix inversion. Okay, and so there are two different approaches which have been compared. One is the 1-bit HHL algorithm. HHL is one of the best-known quantum algorithms. The name comes from Haro Hasidim Lloyd, and it promises, but until now has not delivered, a complexity improvement over the best classical alternatives for solving sparse systems of linear equations. However, and it's a big however, its practical implementation faces considerable challenges, in particular because it leverages the quantum phase estimation, which is currently not cannot be realistically implemented on noisy quantum processing units. So it's more interesting exercise for several reasons we will cover in a few slides. So I won't go into details there because there is something more exciting to see. So one of the exciting thing is that I've been able, and there is an application which I've developed, which is available on my private, on my public, public GitHub repository. You can actually easily run experiments on real IBM Quantum hardware. And this is what is illustrated on the left-hand side. This is kind of a log, what happened. So at the top, I'll see whether I can make it a bit bigger, maybe. Yeah, okay, this is maybe helpful. So on the left-hand side, at the top, you see job ID. So this was actually submitted to execution on the IBM phase, quantum processing unit. And so this simulation run only took about 4 seconds of Qiskit runtime usage. Interestingly, I've applied the same approach as for the sample-based quantum diagonalizations. That is to say, there is a very rough computation of an estimation of the power consumption. So based on the assumption hypothesis, which of course can be tuned, that the said quantum processing unit, the power consumption is around 25 kilowatts. Then multiplying by the Qiskit runtime usage, we get an estimate of the power consumption in kilowatt hour for this run, and it's very cheap. I mean, it's I mean, 4 seconds, it's really not much really. But what's interesting is the simulation was actually successful. That is to say, and you see at the bottom on the left-hand side, when comparing the outcome of the simulation, an actual run on IBM phase with the expected solution computed classically, well, yeah, it does match. So that's interesting. It means that at least for small, it's small because it's only 2 particles, 6 layers, but nevertheless it's run on a real QPU. Well, it works despite the fact that it's not error corrected. So that's interesting. What you see also, I think, in this, do we see that? Not sure. Anyway, we can have more details on the actual GitHub repo. So you can actually, if you wish, after this my presentation, you can have a visit my GitHub repo. The link is there. And so you see I run quite a large number of different scenarios, starting from a humble 2 particles, 6 layers, then 4 particles, 6 layers, multiplied by 2, all the way to 1024 particles, and then beyond. I think the record is 5000 particles, 7 layers. Okay, and I will show you. So the fun part is that you can actually set up your own track simulation, the toy model, because it's fairly simple to from an existing run. So a Jupyter notebook, it's fairly simple to tweak the parameters. For example, on the top right, you see simulation options. So layer spacing, well, usually we keep it that way, 20 millimeters. Number of layers. So this is where it becomes interesting because the team of high energy physicists told me that in practice, when they can reconstruct track particles with around 7 layers, they are happy. So seven is a number of layers which makes sense for a realistic simulation. And the number of particles, so in that case, it's the biggest experiment I've ever made, 5,000. So, but there are from 5 different collision points. So that's why on the n particles there is a tablets with 5 and corresponding vertices, which are basically the coordinates of the collision points. Okay, so this of course it's a toy model. So what happens is that there is a piece of code that simulates the event. It's about trying to then rediscover the primary vertices. Okay, so there are a number of other things like the noise parameters, not the noise of the quantum processing unit, but the noise of the experiment itself. A number of display options, and I move to the next slide. And there are a number of options whether you want to run this purely classically or whether you want this to actually be run on air simulator noiseless or an actual QPU. Okay. And there is something which I include systematically now in all of my developments is an estimate of the consumption of the energy, both on the classical side. It could be an HPC, but in my case, it's a powerful laptop. But nevertheless, it can be estimated. In that case, I use a package which is called EgQCC AI, which is open source. And on the QPU side, I explained earlier on that it's fairly basic, but it does work. I use a ballpark figure for the power consumption of the IBM Cloud backend, and it's tunable, but from an earlier article, I give the references. Capgemini, At the time, it was estimated that the power consumption of a quantum computer with superconducting loops and IBM use would be in a range of 15 to 25 kilowatts, okay? Which is very humble, by the way, as compared to what can be anticipated for fully error-corrected quantum computers. And so don't worry, it doesn't consume as much energy as some of the AI large language models. So that's good. So so this is the layout for the 1-bit HHL quantum circuit for just 2 particles and 6-layer simulation. You can recognize there is the inverse QFT, the quantum Fourier transform. It looks fairly simple. It is simple, actually. Interestingly, the depth is quite reasonable, at least for 2 particles. So that's why it actually works really well. I give a number of glossary of terms for those who just discovered this topic. These simulations pertain to the so-called VELO, which is the LHCb vertex locator, which is a sub-detector, which is closest to the collision points, contains a negligible magnetic field. And the name vertex locator, as the name implies, it's about locating the primary vertices where the collisions occur in the first place. Okay. I don't know how are we doing with time. Could someone tell me how we are doing with time? So I would be
we are very close, Alan.
Okay, so great. I did it in time. Nevertheless, if people want to ask questions beyond after this session, please feel free to reach out to me directly and do visit the GitHub repo. And I wish you a great following sessions. Thank you so much for having me. Thank you.
Thank you, Alan.
Thank you to all our speakers for the interesting presentations. And next up, we'll have engineer Sameh Zaghloul, who is the Chief Technical Officer at Fixed Solutions. Yes, please.
Thank you. Okay. Oops. Works. السلام عليكم. سؤال بقى عشان اتاكد بس ان انتم صحصحين شويه. Sorry. One question to make sure that we are awake. What is the famous quantum algorithm that you know?
Well, it's probably you mean sure, but it doesn't mean that I'm awake.
Actually, we had from your side, Dr. Ahmed, sure algorithm, of course, and BB84 actually. Okay, which is famous, by the way? Is it BB84 or sure algorithm? Sure. Why sure? Because it is dangerous. It is threat. Okay.
Yeah, but everybody's talking about it. Yeah.
Yes, exactly. Okay, because actually the shocking effect that already caused by Shor algorithm when they developed this algorithm something like more than 30 years ago. Okay, he used actually quantum period filing. Okay, to estimate actually or defactor a very large prime number, as you of course you all know, to 2 large prime numbers. So it is very famous because this is one of the biggest threats and brought everyone attention. Because as mentioned previously in previous sessions, Quantum cryptography is one of actually major areas that will be affected by quantum computers. Okay. We heard about Q-Day.
I'm sorry to interrupt, but can you share the screen along with the camera? Because people online, I think we don't see the screen that well.
We'll try, Dr. Ahmed.
Well, if it takes time, then forget about it. We'll follow up later. Excellent.
Okay, thank you. Great. Okay, it worked actually. So solve the second problem. Who heard about Q-Day? Okay, and when is the latest estimate of Q-Day? Today, actually, 20th of May, 2026, actually, it is after 3 years, 2029. So the Q-Day, actually, it is estimated by 2029, where we should have actually something like few thousand logical qubits to solve RSA in real time. Okay, but this is today. Okay, we are not sure about what will happen next week or next month or next year. So the door is closing. وممكن يقفل على صباعنا. On the other hand, BB84. Why BB84? Because quantum computing is not only a threat for cryptography, but it is only also advantage. Charles Bennett and Gilles Brassard, BB. This is the first part of the protocol name, BB. Developed this BB84 40 years, 1984. 40 years, more than 40 years now. And just recently, a couple of months, they awarded Turing Award. This is, as Dr. Ahmed mentioned, this is the equivalent for Nobel Prize in computer science. One question, why Shura didn't get Turing Award and Burnett and Brassard got it? Despite the fact that Shura is much more famous. Okay, because this is the real edge of quantum computer. Actually, we can actually use Heisenberg uncertainty principle and no cloning theory to secure quantum communication in a way that was not available before. So this is a breakthrough in security using quantum. So quantum computing is not only a threat, okay, to our current cryptographic infrastructure, but also a huge enhancement in securing our communication. So this is the main point. So actually, the two sides of quantum computing regarding security, one of them actually is that we need actually to change our cryptographic algorithm, because with short algorithm and the more algorithms to come, okay, current cryptography will be weak. But also on the other hand, we have great opportunity to enhance our quantum security. Imagine here that we have a bank vault, and this is where my valuable data is, okay? And I need to protect my data. So imagine that we have this triangle. I call it triangle of quantum security. What we need to do actually is put our vault inside the triangle, okay? This is a triangle of quantum security. So quantum security is not only post-quantum cryptography and the new family of cryptographic algorithms that you already, most of you know already. This, by the way, this is the type of a lock of the vault. You change the lock of the vault actually with something much more complex, such that even quantum computer actually will not be able to solve it. So this is a post-quantum cryptography. And this does not need quantum computer. Actually, this runs on our classical computer as it is, because this is actually where we are running every systems. Like Dr. Ahmed mentioned previously, classical computers will coexist with quantum computer. No one will replace the other. to post-quantum cryptography run on our existing hardware, like the encryptions that we are using in this online meeting. This is encrypting using HTTPS and RSA, for example. To upgrade it, actually, we'll just replace it with another version that will be post-quantum ready, but on the same classical hardware. We do not do this actually in quantum hardware. Okay, this is the first important part. Okay, and this is, by the way, most of the complexity because of migrations, like we'll see in a few slides. This is BB84 and the quantum key distribution. BB84 was the first one. It was developed 1984, but there is a dozen actually of following quantum key distribution protocol, like E91 actually after maybe less than 10 years. Okay, this is actually how we protect our quantum communication using quantum physics. The theory is simple. The superposition of the qubit, okay, and uncertainty principle beside no cloning. This means that any hacker or attacker actually cannot take a copy of the qubit, okay, and store it, okay, because if it does this, actually, it would collapse quantum state. So the sender receiver will know immediately. So this is the next ultimate level of security actually that didn't exist before. So this quantum communication actually is a method, by analogy again with the bank vault, okay, is how to transfer or deliver the key or the secure code in motion. What about random number generators? In cryptography, either classical or quantum or post-quantum, you need actually random key in all cases. This is classical cryptography. How to generate this random key? You need unpredictable physical source to do it. What we are doing during the last 20 or 30 years actually is we use something called TRNG, true random number generator, where we have some physical sensors to measure noise, magnetic fields, any multiple natural phenomena where you don't have any control. And you combine this unpredictable physical source and you generate your true random keys. The equivalent now is much simpler using uncertainty principle and using a dedicated photon chip to actually generate random photons. And this will be the ultimate and simplest, most efficient random key. So again, this is the most important part here. Actually, this is why we call it triangle of quantum security, because it is not only post-quantum cryptography, despite this is the most critical part, but also securing our communication with quantum communication like quantum key distribution and other protocols, and also making sure that the root of trust, I generate true random keys. Okay. And of course, all of you actually, this is not new. NIST started 10 years ago actually in highlighting this vulnerability. Okay. Even 10 years actually, you didn't have quantum 3 or 4 or 5 qubits. Okay. But it was enough actually to prove the concept of Shor algorithm that was developed 30 years ago on very, very, very short RSA key, of course. So during the last 10 years, actually, there were, I guess, 3 or 4 rounds. TLZ announced the FIPS standards, I guess, last year. So the problem statement is that quantum computers are getting powerful, okay? And the Q day, this is the day when we have cryptographically relevant quantum computers. The estimate today, by the way, today, 20th of May 2026 is couple of thousand logical qubits. 2 months ago, actually, we were talking about million qubits to break RSA. So in 2 months, actually, this is one order of magnitude less. Okay. And again, we're not sure what will happen next week, next month, or next year. There is a famous theorem called the Mothka theorem. It says if you x plus y greater than z, actually, then you have a problem. X is the migration time that you need to migrate to post-quantum cryptography from your existing cryptographic. Okay? and why actually is the shelf life of your data till when actually your data will be valuable or critical or sensitive. And Z actually is the third time. This is the day to Q day, which is how many years from today? 3, less than 3. Okay. Was this the first time actually we do this cryptographic migration? No, actually, this was happening during the last 50 years. There was many milestones where we changed or migrated different cryptographic algorithms. Okay. Now we have the new standard, but this is not the only standard that we'll see together. Okay. And we have till from here actually till Q day actually to do the migration. Why this is it a little bit complex? We'll see in a few minutes. So this is not new. Migrating or upgrading my cryptographic infrastructure is nothing new. Actually, it happens almost every 10 years during the last 50 years. But now the scale or the complexity of migration is a little bit different, and we'll discuss this. So regarding standard, what everyone is doing, of course, NIST, the top active more than 10 years, different 3 rounds at least, till they reach its FIPS 203, 204, 205. Okay. But this is not the only standard. Okay. Because actually we have parallel standard in the European Union and they are not using NIST standards. And another standard, confidential, of course, in China. Okay. They develop their own proprietary cryptographic algorithms, but it is not public, of course. And you have also evolution and progression in the Middle East, in Saudi Arabia, United Arab Emirates, and Qatar, where they are started to putting their deadline for completing quantum readiness assessment and putting a plan for the migration. And even they started developing their own cryptographic version of EgQCs. Okay. Which is, by the way, actually in Egypt, we have actually cryptographers in all universities actually is one of the very, very strong cryptographers worldwide. So we can do this very easily. Why this is different between from region to region and country to country and continent to continent? Because it is security, actually. So everyone actually is moving his own direction. So a complete, but this is normal, by the way. And all large organizations, especially in defense and government, use their own flavor or classical cryptographic algorithm. And the same actually applies to post-quantum cryptography. Okay, another question. Harvest now, decrypt later. Is this term familiar to anyone? Okay. After 3 years. Exactly. This is the current threat, and this is not happening today, and will not happen actually at Q Day, which is now 2029, by the way, till now. Okay. But this is already happening during the last few years. An attacker actually take a copy of both encrypted keys, encrypted data, and storage. Okay. And will be able to encrypt it actually a couple of years later, which is now 2029. Okay. One question, and this is regarding to the hackathon actually challenge. If I am securing my communication using quantum key distribution, for example, will the attacker be able to do this? Do not answer, actually. No cloning theory. If I already was securing my communication between the sender and the receiver using quantum channel, using something like BB84 or any quantum key distribution or equivalent, will an attacker be able to get a copy of my keys, encrypted keys, without being noticed? Because no cloning theory. Imagine the qubit actually is a flipping coin. As soon as you try to measure the coin, actually it will be 1 or 0. So sender and receiver will know. Okay, and cancel this message and restart again. So that's why actually this is another quantum communication is another level actually of security actually available only because or mainly because of quantum. Okay. What about Q-Day? Q-Day actually the same attacker actually will be able actually to collect the encrypted key and collect the encrypted data and decrypt it in near real time. This is what will happen. Okay. So what we need to do first, actually, I need to know what I have. What are my cryptographic algorithms that we are using? Okay. Usually called the cryptographic inventory. Okay. And also do a public infrastructure health check. This is actually the central authority that I am generating the keys, the random keys or true random keys, and distribute the life cycle, the keys, and manage the life cycle of my encryption keys. This is part of the root of security. And also do some risk assessment. Risk assessment, the simple example that our online session today encrypting using RSA, which is not quantum resistant. Okay. One question here actually is the data shared on this online session are sensitive data? Today, no, of course. But what if it is another organization using the same platform and doing some conference call discussing internal details with different level of security? In this case, will be sensitive data. So I need to migrate action. So this is what we mean by risk assessment. I have a vulnerable component, but what is the sensitivity or criticality of the data that protected by this encryption layer? It is, if it is sensitive, I should put it as a priority. If it is not, I should delay it later actually for a couple of years, even after Q-Day. One of the things that each organization should do is what we call readiness or maturity assessment. Okay. We have 9 dimensions with different weights and different maturity level. Okay. The objective actually is each organization should assess current situation. Okay. Do I have a full cryptographic inventory? No, in progress, not yet. For example, planning. Okay. Did I do we have risk assessment for the even partial part of my cryptographic inventory? And what about the technology and the crypto agility? Okay, crypto agility, actually you'll discuss this in detail. This is actually how flexible or difficult I can change my cryptographic algorithms. If it will take time or will take just upgrade, collect, next. Migration. Do I have a complete migration plan? And actually, this is the critical part. And also, the technology stacks that I'm using some open source component and commercial components. Regarding the commercial component, this is the major issue. Are my suppliers, software and hardware, already has quantum cryptographic technology or not yet? Because actually, I'm tied with them. And regulatory and compliance, like a national strategy and regulation. In the previous slide, when we talked about NIST in US and talked about China, talked even about Middle East, they have already published this national quantum strategy and the regulation that mandate actually the migration to post-quantum cryptography. Couple of reasons now. Actually, this is being done this year in Egypt. So we have actually our AI national strategy published maybe 2-3 years now. This year actually they are finalizing our national quantum strategy. So actually we are on the right track. So this is very important, regulatory and compliance, and awareness and workforce training. Why do you think actually I bought the maximum score? Like our session today, actually, and all the previous sessions that's done by Alexander Live. So this is very nice example, actually, of the awareness. Why you are here, actually, because you're already starting, not this year, last year and previous year, actually, to be aware of quantum computing and its applications. So this is very important part. This was not the case, actually, when I started discovering quantum computing, actually, maybe 8 years ago. Okay, no one was talking about it, but 4 or 5 years, a little bit. The last 2 years, it is increasing, and you are a very good example for this. Okay, why you need to do this, actually? Because I need to know the weak point to improve it and get something actually to move forward and move to the next steps. Okay, what is the landscape of quantum cryptography? I guess anyone with some cryptography background will know that we don't have one family of cryptographic algorithm, multiple families, each one has multiple flavors. So actually it is not ES, it is not RSA, it's not elliptic curve. No, it is multiple families, including also digital signature and cipher protocols and like TLS and SSL. Okay, so actually this comparison actually will find different families with different flavors or variants of each cryptographic algorithm. So actually it is building cryptographic inventory is not a trivial or easy task. It will take some effort, like we'll see now. Okay. From previous projects, okay, a typical data center for a medium or large organization will have something like 100 virtual machines or servers. Each one typically will have 20 to 50 distinct algorithms. Think actually from application layer, the proxy server, firewall, proxy server, application servers, okay, a web servers, application server, middleware, okay, service bus, workflow engine, database, operating system, network layer, storage layer. All this layer from top to bottom, the 7 layers that we all know, actually has different cryptographic algorithms in different components. I need to discover this. So we are talking about typical mid to large organization actually will have hundreds of unique algorithms that I need to collect to build my cryptographic inventory, then do a risk assessment. Risk assessment, as we mentioned, actually, what is the data sensitivity or importance of the data protected by this cryptographic layer? And put the priority, because the migration will take some effort and some time. So I need actually to start with the critical first. That's why it's risk assessment. One dimension very important actually is we don't have one tool actually to build the complete entire inventory, because we have data in motion, okay, like the traffic actually in our online call today, and data encrypted at rest, stored in disk, database, whatever data repository. So post combination depends on the application, the operating system, the technology itself. So usually we discover that we need to use multiple components in different layers to detect my cryptographic algorithm. The worst case scenario here is if I have, during static code analysis, my application, if it is custom built, okay, use the hard-coded cryptographic algorithm within part of the code. This usually part of the difficult component actually to migrate, because actually you need to refactor the code in order to migrate, which is usually difficult, not because of replacing an algorithm with another algorithm, though this is very easy, but actually to make your application crypto agile. Crypto agile means that if next year actually we have a new version of cryptographic algorithm, actually I should be able actually to do the migration without refactoring and refactoring and refactoring. So if you are lucky, actually we'll cite the software engineered clean codes, okay, where every concern or separated, and or cryptographic algorithm actually separated in different modules and configuration files. So just replace and rebuild it with code. But this is not the real world, of course, actually. That's why actually post-quantum cryptography is not all about cryptographic algorithms, It is about of complexity of refactoring or enhancing your architecture, because this is exactly what will happen. You need actually to rectify or refactor your architecture and some of components of your code, okay, to move to the next step, actually migrate your cryptographic algorithm and be ready for the frequent migration. Because as you mentioned, NIST was working on this PQC standard during the last 3 years or 3 rounds. The last version, FIPS 203, 204, 205, published late 2024. But maybe within a few months, actually, you'll have another version, because the people actually are active. They are developing a new algorithm, discovering new vulnerabilities. So it is dynamic. So cryptographic agility is one of the important factors that we need to discover. Ideally, one of the standard format, actually, this is just a schema definition, cryptographic bill of material, CBOM, actually. Commonly used during the industry, all over the industry, okay? Just guidelines, actually, how to store your inventory data, okay? And I guess we'll have some very, very high level example. So this is very small example, of course. This is very brief example for what should my CBOM or cryptographic bill of material look like. I have a web server running this technology, encrypting using RSA and using OpenSSL 1.1, for example, and the key length, of course, it is very important, 2048, and etc. Okay, and the recommendation, of course, you all know RSA should be migrated. This is back-end DPI, okay, encrypted also with RSA 256 using Java GW tokens, okay, should be planned also. This is database encrypted with ES256, which is currently, as of today actually, okay, considered post-quantum ready. But this is today actually, okay. Till someone like Shor, for example, discover some very powerful algorithm actually to break RSA. By the way, actually, why ES128 is vulnerable? Because of Grover algorithm, the second famous search algorithm actually. It reduces the complexity of ES by much far. So this is the minimum actually today actually can be considered post-quantum and so on. Okay. One example also related to risk assessment. For example, this is logging service. If this logging actually for performance metrics and web logs and application logs does not need does not contain any sensitive data, just performance information, I use it for monitoring, system and capacity planning. Although that it is already not post-quantum ready, I can put it lowest priority for the migration. So this is another dimension very important for planning the effort. Okay. So how we calculate our risk models, okay, or quantum risk assessment, this is the most important, second most important part. Actually, third most important part. First one, like we discussed, my readiness, the different dimensions. Am I ready? Where is the weak point? Where I should complement? Okay. Second, lot of effort actually to build my cryptographic bill of material. Okay. Third is more or less simple. Okay. But need to be done carefully. This is GRC-like actually risk assessment. Exactly. I am doing GRC for quantum. Okay. So that's why you call it quantum risk assessment. Okay. You will see actually that we have a list of different methodologies and different frameworks. Part of them actually as industry specific, like banking. Okay. But I personally prefer actually the examples that we'll use actually is not Mosca theorem that we discussed, because this is binary classifier 1 or 0, x plus y less than z or greater than z. No, we use adjusted version. We call it quantum adjusted risk score. Okay, built on Mosca theorem, but it generates the risk factor from 0 to 1. Let's take an example. This is the famous Mosca theorem. X plus Y should be less than Z, so I'm okay. Greater than Z, I'm in trouble. Okay. And this is of course the elements that we should collect. Okay. With this different standard, the regulation actually mapped to the previous slide. Let's have a look, very quick look at the equations. We have X, Y, and Z. Okay. Now we are calculating T, S, E, and each one has weight. WT, WS, WE. Okay. T is the timeline risk. This is the common timeline risk that we've talked about, X plus Y. But we converted actually to an equation to generate something between 0 and 1. So this is the first part. This is for the T. The weight of T actually will in the next slide. S is a stability risk, low, medium, high, critical. As we discussed, our data actually today actually is not sensitive. So the risk will be low, something like 0.1. But in another organization, another type of online meetings actually can be 1 or 0.8 or 0.9. Okay. 3, exposure risk. Exposure risk, this is related to harvest now, decrypt later. Is my data exposed to the internet, public traffic? So any attacker actually can harvest or copy my data, store it, and decrypt it later, harvest now, decrypt later or not. So this is another measure. Okay, it is here binary, 0 or 1. 0 if it is protected by PQC, 1 it is vulnerable and already internet facing. Okay. For example, actually, this is 0 between 0 and 1. A score, risk score. Okay, like the readiness score, but this is from risk perspective. The minimum is 0, the maximum is 1. What about the weights? There is some okay, commonly agreed upon weights per sector. So finance, for example, the weight time 0.4, while for IoT it is 0.5, higher weight. Okay, cloud service, general baseline, no. Sensitivity, of course. So we talked about S multiplied by T multiplied by E. Okay, and each one of them has the weight factor. Okay, so the total, always the total will be something between 0 and 1. So this is some example. Okay, core banking, as we expect, of course, will be critical. And on the other spectrum, actually serverless function. Serverless function, serverless actually does not have just process data, that does not store anything. So actually, even it is not post-quantum ready, it does not have any data at all, actually, not even sensitive data. So actually, it will be very risk score, and I can keep it for many years actually till the normal migration. Again, this is a long-term plan, couple of months, maybe couple of years. So I need to take some immediate actions. Adopt a hybrid strategy. Hybrid strategy, like we'll see actually, is that I cannot migrate everything at once. Okay, so I need to start actually with putting something like isolation layer to separate external from internal traffic, and also start with the critical assets. Okay, and actually work on the organization level, because this is really the bottleneck or the barrier. The organization should work all the organization work, and this is directly not the IT only. One quick example related to hybrid approach, okay, which we call a proxy pattern. Proxy, we all know proxy layer. Actually, I'll add just another, I replace my proxy with a BQC ready proxy, such that my external traffic always is encrypted with one of the post-quantum cryptographic algorithm. Okay, so at least I mitigate the harvest now, decrypt later, till I migrate all my internal system later, maybe next month, maybe next year. Okay, this is the upgrade. Okay, and also actually in a later phase, actually I can introduce the new advantage of quantum computing actually in quantum communication. For example, securing the communication between my main and backup data center, something like that. Okay. Final slide summary. Cryptographic inventory, just summarize. Cryptographic inventory risk assessment, two most important steps, and roadmap. This is the three steps actually that I should do. Then the actual migration. And the migration actually is not simple task. This is, by the way, this is why actually this is complex, not because of cryptography or post-contact cryptography, but because it is complex migration project. So usually I will start with the inventory and risk management in the plan. This is short term, 1 to 3 months. Mid-term, start with a critical system and do pilot migration, maybe 3 to 6 weeks. And then long term, actually, I should plan, like we have seen, all the migration for all my infrastructure within the next maximum 3 years. We don't have 3 years today. Actually, we have less because today is mid 2026. Okay. This was a quick summary. Okay. Any question? Okay. Very important update before we go to the break. Okay. Every one of the 5 teams, right? 5 teams should have uploaded their presentation and get a code to the GitHub. Okay. And okay. And should be ready actually by downloading all the presentation on this machine, this PC, okay, before the end of the lunch break, because we'll start immediately in presentation. Each team will take something like 10 to 15 minutes. So everything should be ready, downloaded, and we should go fast just to get some time actually for the evaluation. So the lunch break for the hackathon members is not a really lunch break. It is partial lunch break. All? No. As you agree, every team has to agree actually on 1, 2, all the team, whatever. But it must be kept within 10 to 15 minutes. Any final comment, Engineer Yusuf?
Thank you again very much, Engineer Samah, for chairing this industry academic summit. It was wonderful to listen to all the presentations. Thank you to all our speakers. And we wished, for those who are participating online, wish you were here with us, but we'll see you maybe in 3 months. Thank you very much.
وات ايفر، يعني واحد اللي هو الفا بيتا مش واحد يبقى الفا، مش مشكله. انا هنعمل هم ولا الفا بيتا جميل. لا ما انا قصدي عشان اوكي تمام. بس اوكي تمام خلاص مش هنستخدم بقى، هم اوريدي عارفين مسؤولين، بس انا الابلكيشن مكتوب 1 2 3. Very important team. Each team has 12 minutes because of time constraints. Good luck.
Good evening, everyone. We are Team Beta, and we are thrilled to be here today, present our project Quantum Dementia Classifier. Today, Dalia will present the introduction and the problem statement, and my teammate Ines will explain to you the classical and quantum pipeline. Then our teammate Hanin will present the business analysis and finally future work with Dalia. All of this is under the supervision of our mentor, Dr. Maha Mutawa.
Firstly, let's talk about dementia. Dementia is a neurological disease that affects brain and cognitive abilities. And our model is to improve the ثانية معلش. Is to improve detection early. Okay, is to improve detection early and to reduce the يعني we worked on 150 subjects, sorry, and aged between 60 to 96 years old. My teammate Ines will
so before we know our results, let's go through our main pipeline. So first we apply some pre-processing to check our data and know our main distribution. So after that, we apply two main pipelines, the classical pipeline, in which we use the 8 main classifiers with 5 cross validation, 5-fold cross validation using the matrix accuracy F1 score AUC. The second pipeline, main pipeline, is the quantum variational circuit. So we designed main for variational quantum circuits using angle encoding with Penny Lane Adam optimizers. The last thing, we will compare between our performance between the classical pipeline and the quantum pipeline. So in the pre-processing stage, where we first do our exploratory data analysis by visualizing the data and see our distributions as shown in the as shown in the slides. If we notice that our class distribution shows the imbalanced data set, for the pre-processing, we check if there is null values or any duplicate values. There wasn't any duplicate values, and there were small features with small null values, which were filling with the mean value. After that, we defined our main features, 10 main features, which shows which help us train our models and detect the early detection of the dementia. So these features are mainly like a clinical features as a biomarker for dementia. One thing also that our subjects have each subject in our data set have more than at least two visits. So to ensure that there is to avoid data leakage or overfitting, we made sure that each visit of the single subject in the set of splitting. So for data splitting, we make a subject-based splitting with 70% of the training and 15 for testing and 15 for validation. Now for our classical pipeline, we use the eight classifiers. As we shown that accuracy, for the best accuracy shown, test accuracy, we're shown with the naive bias. And for the cross-validation accuracy, it was with XGBoost and the random forest, achieving 91% for the cross-validation accuracy. Okay, and as we shown that classical models shows very small computational times. And also it's better to see the visualizations of the confusion matrices. Here are our three top classical classifiers. If we notice that they miss in classifying the demented classes, which shows that they are not able to detect or learn specific features, and we will see later. That's why in this case, that's why we converted and tested our quantum models. So before we begin to our quantum models, it's very important to ask these questions. How can we build our quantum model? To answer this question, we set specific criteria. First criteria is entanglement capability. In this criteria, we set three main architectures from the literature. First one is the linear and the ring, as shown here. This is the ring design, and all-to-all, it's similar to the fully connected layer in the classical models, classical neural network. Our four main designs mainly utilize CNOT connectivity between the qubits with linear design, and the second one is the controlled rotation gates, and this will come our second criteria, which is the expressiveness. From literature, we can it said that prioritizing using controlled RX is better for showing more expressiveness for the circuit. After that, we did apply our third variational quantum circuit with ring design, and the last one was all-to-all. It starts with angle encoding. So as we know that we have 10 features, for each feature is 1 qubit, and we simulated them using mini-LAN. The second layer is the variational layer. So we started using the RY and RZ per qubit. And then we applied our entangling connectivity on the qubits. So with optimized via Adam using mini-LAN. The last one is measurement using 3 qubits, as we have 3 classes using Pauli Z expectation value. and we uses the weighted gross entropy. So this table summarizes the main gate counts and the number of parameters. So for this is our quantum results, as we can see that they are detecting some dimensioned clauses as a converted, which shows similar features, and that quantum models are able to classify or learn specific features in this clause. We can see in cross-validation accuracy that that it shows 47% and 48% in the second architecture and the fourth architecture. And if we notice the increasing in the cross-validation accuracy, as as the literature said that the ring and all-to-all shows better accuracy. Next. So after we know our results, we decided to tune our third variational quantum circuits to be tuned to increase the depth of the circuit to 3 layers. So that makes us that increased our number of parameters to about 195. Next slide. For our tuned circuit, it shows the increase in variational cross validation accuracy about 77, 77, as we can see in the fold 3. And for the two folders, if we can see that they are show the same accuracies, consistent accuracies, and that suggests stable learning during the training. Next slide. So to finalize, we can see that there is a performance gap between the classical and the quantum about 40 percentage point. The best one for the test accuracy is 52, and for the classicals using naive bias, we achieved 93. And the second thing is that entanglement topology matters, as we can see as we change the entanglement design, the result changes. Also, there is something about the there's also compromising between the circuit design and the computational time. So as we increase the layers, the computational time, so you lose something against enhancing something else. And finally, with our business analysis and future work with Engineer Hanin.
Finally, the business value of our solution: early dementia detection using MRI and AI. Target clients: hospital, radiology centers, institution, companies, pharmaceutical firms, and government healthcare system. The business value is earlier diminution detection, reduced for workload for doctors, and lower treatment costs. Faster, more accurate, and consistent detection, support for elderly care needs. Summary: in AI systems that analyzes MRI scans to help doctors make faster and more accurate decisions in early dementia detection. And future work will be presented by Dalia.
Let's talk about future work. We already used softmax, and we have two options to increase the work with run on real hardware like IBM Quantum, and work with hybrid classical and quantum models. Thank you for listening, and questions are welcome.
Hello everyone. We are Team Gamma. Our topic today is about the quantum dimension classifier and does the quantum computation or quantum computing improving the early detection for the dimension or not? No? Okay. The dementia is one of the worst diseases that facing the millions of people around the world with no medicine, no care. So the best solution that we can do today is the early detection for the disease using the MRI scans. The features that we can get from the MRI scans to classify the patient as a demanded or not or non-demanded with a disease. So why it matters to use the quantum because the early detection is make it reduce the budget of the treatment and make the percentage of the treatment for the patient is very high. Now with the data overview with Engineer Abdurrahman.
In our analysis, we used information published on Informatics in Medicine Unlocked. Then it was re-uploaded on Kaggle, which we used to analyze. It has 373 MRI scans, 10 features, and 150 unique solutions. 150 unique people. We divided them into 3 classes: demented, non-demented, and converted. Our goal in our analysis was to to diagnose them early, to find to ease their experience and to slow down their symptoms. Data processing has a part that's the data pre-processing, which includes handling labels. We convert demented and converted the patients into positives. Then we split their data into 80% data that we trained the machine with, then 10% for testing and 10% for validation. We do these splits using the patient's ID to prevent data leakage. Thank you.
Okay, we tried 2 different classical models as baselines. The first of which was a small neural network. It was only 2 hidden layers. The first of which was 16 neurons, and the second was only 8. And it of course had one output, which was either positive or negative. It's a binary classification problem. The training was done using a learning rate of 10 power negative 3, and we used a dropout rate of 30% to prevent overfitting. We got an accuracy of 98.6% and F1 score of 98 and UC of 99. We also tried SVM. We used the kernel of RBF, radial basis functional. It got an accuracy of 96.6. Then if the results so good, then why did we try quantum? First, due to the richer feature space, with only 8 neurons, with only 8 qubits, we could do 256 dimensions. And because that set size is so small, like having small number of features and small number of data points, having quantum computing would be perfect. Quantum machine learning would be perfect. Next. Okay, quantum solution would be with Hassan.
Okay, do you hear me? Do you hear me?
Yes.
Okay, I will start sharing.
Okay.
Is share?
Yes, we see.
Okay. We start about quantum support vector machine. Our data processing is normal data processing, scaling standard scalar, but here is the catch. We want to try different qubits and see how quantum vectors in different. So we used principal component analysis to reduce our dimension. Then I use angle encoding using min-max scalar to avoid angle aliasing. Also, we have kappa tuned, and we will use it later. Okay, here is our quantum future map. 2 qubits, 4 qubits, 8 qubits, and all future. We realize in small qubits or in small number features, it's just the best feature map, just rotation, phase estimation rotation. Although when I use all futures, entanglement play part here, because when I use reduced, I use the results that come from principal component analysis, which get independent columns. So I don't need entangled part here. When all futures, entanglement give me a better result than using a single Z rotation. Here is a results of our quantum support vector machine and RBF function. We realize in RBF function, L separators are more curvy than quantum because RBF function is scaled to infinite dimension of space, so it has more opportunity to do some curvy function. Although the quantum, it is limited to 2 power number of features. That is what we appear here. But still, quantum kernels did a pretty good job like classical ones. We realize here, I tried 5-fold cross-fold to test on different part. We realize here when increase number of features is accuracy increase, but overall RBF function slightly better than quantum kernels. And we see the variance is become less is larger than the variance in RBF. So that means generalization in RBF function better than quantum ones. But there's here a catch. Quantum here we use a simulation, but in hardware it will be there's noise. So sometimes they use sanitization pipeline. Sanitization pipeline have 3 cases to make sure the kernel matrix semi-positive definite matrix, yani all eigenvalue in the matrix greater than 0. The diagonal of the matrix must be 1. Also, the matrix must be symmetry. We will continue with variation quantum circuits with IHAM. Thank you. I'll cancel share.
All right, so for our specific VQC setup, we use amplitude encoding with 5 qubits and 3 layers analysis. We train the model over So we train the model over 60 epochs using Adam optimizer as a baseline. This pure quantum approach, 63%. Okay, this pure quantum approach, 63%. And that's very low. I know that. But so we use another model right now. That's going to be the hybrid one. So we use the classical features. So we use the classical features with 11 inputs feature right now, and down there with 4 features. We use the quantum feature map with 4 qubits right now. And it got an accuracy with a 94%. That's gonna be a great one. So we use the comparison and summarize what we see right now.
So as we see in the classical one, the neural network was an 98%, and the SVM was 96%. That sees that the neural networks was great more than the SVM. But in the quantum one, as we see, the VQC was struggling at 63%, and the QSVM and the hybrid was approaching a high percent, with the first one 98%, and the second one was 94%. And that's the end of the presentation. I hope that everyone listens to that. Thanks for everyone, sir. Any questions?
Yes, I have a question.
All right.
What tools did you use to draw your circuit? Is it penny lane or Qiskit?
We use Qiskit version 2.
The version here is Penny Lane, but I use when I train Qiskit. But I found the Penny Lane more good to our format of our presentation here.
Okay, that's good. In your presentation, you mentioned that you didn't use any noisy, but why you didn't use the noisy simulate?
I didn't find because the first try, and I'm not planning for testing on hardware. But yeah, if I test on hardware, I will use sanitization pipeline and the noisy part.
My point is you can use noisy models on without running on real hardware.
Okay, understand. I didn't. I forget that, but yeah, that is really good to try. Yeah.
Yeah, this will give you maybe near accurate maybe information. This is the only question. Thank you. Good job.
Thank you.
Assalamu alaikum. In the name of Allah, the most gracious, the most merciful. Today, I'm going to talk about quantum cybersecurity. Most people think cybersecurity is about passwords, maybe strong passwords, maybe fingerprint locks, maybe changing your passwords every 3 months because some company got hacked again. Humanity truly turned 1, 2, 3, 4, 5, 6 into a global security crisis. But behind everything we do online, banking, messaging, shopping, there is one invincible thing protecting it all. It's encryption. Encryption works because today's computers would take an extremely long time to break certain mathematical problems But there's a problem. A new kind of computer is coming, and it doesn't play by the normal rules. Okay, what's the problem here? When they discovered the Shor's algorithm, the classical encryption uses classical mathematical operations. So the Shor's algorithm doesn't talk in zeros and ones. It talks in qubits. It has more than 2 values. So that made a big headache for people who work in security field. Harvest now, decrypt later concept. It's a concept where there's an interceptor who intercepts the decrypted messages and stores it. In nowadays, they take like 3 years to decrypt these messages. But when the quantum computers emerge, they will have the ability to decrypt it faster than ever. Okay, a comparison between the classic algorithms of encryption that it uses mathematical operations. The new quantum algorithms like BB84 protocol uses laws of physics, not math. And it's the advantage of this that computer power can't outrun this algorithm. But if we came to the classic encryption algorithm, it takes forever to decrypt these data. In the interception mechanics, when we talk about quantum, it has like a radar that signals when anyone is watching. If there's an adversary that is collecting the data or watching, it stops this immediately by breaking the communication between the two adversaries. So here is the scenario. We have Alice and Bob. Alice wants to send Bob a message, okay, using quantum communication. It uses qubits instead of normal bits, zeros or ones. When the message is sent, every time there's a unique key, a unique secret key that is exchanged between the two, Alice and Bob. But what happens if there's like a third person in the communication, Eve? If he intercepts the communication, what happens that the message arrives to Bob broken, not complete. So Bob knows that there's someone in between is listening to these messages. So the communications cuts immediately. And now Anas Hisham will discuss with you what we have done in our project.
Hello, everyone. In our project, we simulated this process using a protocol BB84 to secure quantum channel. Here, how it works in a simple terms. Alice sends random quantum signals, and Bob tries to read them. Sometimes their choice match, and sometimes they don't. The matching results become a secret shared key. Then the key check for unusual errors. If too many errors appear, it means someone may have intercepts the communication. Why this is powerful? What makes quantum cybersecurity different is this. Traditional cybersecurity tries to make hacking difficult, but quantum cybersecurity tries to spying or dictatable. That's a huge shift. Instead of hoping nobody breaks the lock, the system itself swarms you when someone even touches even the door. In our simulation, when no attacker was present, our communication stayed accurate and secure. But when we introduced an eavesdropper, error rates increased immediately. The attack exposed itself automatically, which is refreshing, honestly, Most cyber attacks today stay hidden longer than university group project freeloaders. We used Python and IBM Qiskit and Qiskit Array and NumPy. Thank you.
Any questions? All right, thank you. What? And the code using Qiskit. And we used a predefined arguments. It was predefined. It was an example scenario we made in the code. Okay, thank you.
Hello, everyone. My name is Halima, and our team is Alpha Team. Okay. We will talk about today about the quantum K distribution. Okay. We built a complete end-to-end simulation. Okay. For two major quantum protocols, BB84 and Cascade. Okay. First, we will talk the agenda. This is the agenda, our agenda for today. First, we will talk through the project overview and architecture. Then we will explain the three pillars, and we will do code deep dive. And finally, we will share with you the results and experimental. Let's start with the first part is project overview. We designed a modular simulation suite. This means our code is organized in separate clean file to make it scalable and easy to understand. So what we did actually build, we create 5 core Python models. QuantumPy contains the real quantum circuits and gates. Then BB84 and E91 implement the 2 core protocols. Third one is handle the cryptographic post-processing like error corrections, and nearby runs everything. In total, we 2 protocols and 5 models and 7 different test scenarios. Test scenarios cover all project pillars and stretch the goals. Finally, let's look our design principle. First, we use real acoustic circuits. Every operation like qubit preparation and measurement use real quantum gates. This means our code is ready to run on real quantum hardware, not just simulations. Second, we have a modular architecture. The quantum parts are separated from the classical crypto parts. This allows both protocols to share the same efficiency tools. Second one point, our second part is the balance, and Carlos will talk about with you. Thank you.
Okay, hello everyone. I'm Carlos from Team Alpha. We now will talk about three pillars of our project: key exchange, EFAS detection, and secret key distillation. Okay, we have here BB84 and E91 protocols. Each protocol has a syntax or mechanism in its work. BB84 use a mechanism that each generate bit and basis and then compare it between Alice and Bob. If it matches, then the protocol is successed. If there is penetration, it will be detected through QBR 11%. In E91, we use P bell pair to generate our qubit. Then we compare it between Alice and Bob from the same source of generation. The mechanism in BB84 is prepare and measure. The mechanism in E91 is intelligent base. Security proof of the BB84 is 11%, while in E91 is mathematical inequality called SCHSH upper than 2.2. Okay, pillar 2 now we have BB84 QBER detection. If there is interruption, the full interruption will be approximately in percentage to 25%. And if there is any penetration, it will be above 11%. In E91, the penetration is less than 2.2%, and the maximum penetration or intelligent broken is 0% approximately. Okay, pillar 3, secret key distillation, is three phases: sifting, error reconciliation, privacy amplification. Sifting is compared between bases of Alice and Bob. If it equal, then there is no aborted or penetration occurred. Or error cancellation, flip error, it changes 0 or 1s to be equivalent to remove any error. Privacy amplification, it shortages a key to make it more secured through SHA 256. Now my teammate Yusuf will continue with you. Thank you.
Okay, this slide we will explain how BB84 work step by step. Here we have Alice and Bob. Alice creates random bytes and pieces, and also Bob create random value, bytes and pieces. Okay, the qubits are sent through cascade, and also after that QBER is calculated. Okay, if it lower than 11%, it will be secure. If it more, it will be unsecure. Second slide. This slide explain crypto engine cascade algorithm is used to fix or find any error in code between Bob or Alice. Then privacy amplification use SHA to 256 hashing to make the final key more secure. Second slide. This slide we will speak about the result and output. Here in the slide, QBER after calculated 0.0%. This means it is secure. And the next one, QBER, is 24%. This mean is unsecure. and E is algorithm E91. Here, if it more than 2.2, it will be unsecure. And here is equal 1.55. It mean it secure. Last thing, the project have 5 Python models, 7 tests, and cascade. And this is the name of file main.python, and that's thanks.
So Assalamu alaikum. We will present inshallah the quantum simulation for chemistry challenge, which is a CO2, which is carbon dioxide. And this work will be done with help of me, of course, the first one, and Dr. Asma, and engineer Hasna. So the question is, how to think about solving such a problem in our daily life? Carbon dioxide is having a lot of, bounding issue. We will try to think like a computer or a quantum one. So the idea is to get into 2 mere steps and the final evaluation. The first one is humiliating encoding of CO2 and get into some optimization using 2 methods, the QVE and SQE. And the key idea is looking into the process in general. We have a little slide of, a problem, which is accuracy and computation efficiency and scalability. Looking into our diagram here, we have a molecular humilitation preparation like simplification and try to make an active space selection. So this figure above us will make a summary of our process in general. Like we used VQE and SQD and the hybrid one, and finally making a sampulation. So what is the difference between the VQE and SQE? SQE is the modern one of the VQE. SQE is using the sampling methodology instead of the old one, VQE. Steps in general and simple words. We used the molecular humilitation generation, and then we make a qubit mapping. Then we used the ANSYS preparation, beyond quantum sampling, and classic optimization and diagnosing, and finally performance analyzing. So what we have done, what framework we have used? We used, I guess, 4 framework, starting by quiz. What is it? Cascade, yeah, and the cascade nature, and finally we get into some NumPy calculations. Okay, so what we have done after using the casket, we give into hamulation step and some basic set, which give us the ability to use the energy starting point of CO2. I guess all of you are looking into our result, and this is the key point. So into when we look into the result, we tried the two methods with its optimizations, and we have done like UCCSD and with some optimizing, and we finalize or conclude that the most one had been done with most accuracy is SEU2 plus SPSA with little noise. And the most important thing about the SQD sampling is when we do sampling, is sampling with much shot will have a less accuracy or more accuracy. And from this diagram, we used starting from 17 dimensions up to 20. And when we add some shots, we less the loss or increase the accuracy. The same here for our VQE, this FCI. When we look at the overall figure, we see that if SU2 plus Cupla has more accuracy and less less loss. Same for here in our diagram. And in simple words, we tried with simple computation in computer science and quantum computing to use Casket, use two methods with its optimization. And we finalize that the SQE method was the optimizing with, how can I say it, SPSA, has the final and most accurate and more likely to be like the old traditional computation. Thank you. Yeah, yeah. We have uploaded our work in GitHub. Yeah, Casket and Casket Nature. Casket and Casket Nature. And yeah, let me get back. But to be honest, while using a billionaire and circuit, we have such a problem. While implemented, it take a lot of time. So I make a similar alternative by using Casket and Casket Nature, and I guess there is a third library, but I don't remember it, related to IBM, which makes the computation less time. Yeah, but the final one and the final uploaded file is Casket Nature, and Casket. I didn't remember the real name for it. The timing for the final project and the uploaded take down from around 1 hour till I guess 15 minutes. We did it. Any other questions, please? Other questions?
Alhamdulillah, I congratulate all the teams on their presentations. It was very nice to watch the presentations and see the work you did. Congratulations, you're all winners. So we'll take a few minutes and then announce the results. Thank you all.
Assalamu alaikum. Till we get the final evaluation for your projects, actually, first, thank you very much for doing this great job, actually, in a very short time. Okay. Now, actually, we'll have quick discussion, okay, about your impression and the next steps in after the hackathon. Okay, who would like to start? Oh, yes.
نعيد من تاني. Alhamdulillah, I have been inspired by all the teams has been presented here. Okay. And from my upcoming plan, Alhamdulillah, I have been mentored by a professor who's called Nawarg. He's specialized now in quantum computing and quantum physics in general, and attend some courses in quantum computing like IBM Portal. Quantum computing, and get more depth in chemistry, which isn't my best subject in my world. I didn't like it, but okay, I will try. That's it.
Great, thank you very much.
Welcome.
Need more time. Okay. Next time we need more time to arrange the team to work more, and this is not my branch. I am more medical and more pharmaceutics. I thought in the in next participations or the applications note they send, they must put our branch, because it's very important. I can't work in something I didn't, it's not my main topics. I prefer to mix the teams according to our topics and our major topics, yes.
Exactly, actually, but again, the main idea of the hackathon actually is to do something challenging in short time.
It is different. I swear it is different. I don't like chemistry at all. Next.
I only have an impression that I'm little disappointed because we couldn't finish our work. We didn't get the results that we hoped that we see, and we barely slept. We've been working 24 hours. We had more than 3 or 4 meetings, and I can say that my team didn't do their job, but still we didn't get the...
They did a great job, by the way.
Thank you.
But again, this is the main idea of the hackathon. And by the way, this is a pre-hackathon or mini-hackathon. Because actually, I guess we have a second mini-hackathon within 2 months, July, before the final hackathon. So this is preparation for the final hackathon.
6 hours or 10 hours.
But you have, I guess, you have approximately 2 days. Actually, 19 hours.
No.
19 hours.
No. No, not. We only have one meeting with our mentor.
This is 19 hours, huh? 19 hours, huh? Of course, yes. Okay. But again, yeah, this is the main idea actually is exactly. Oh, don't worry, actually, you did a good job. What else? Anyone has other comments?
Okay, so I didn't have the chance to participate this time, but I'm planning to do so, inshallah. But having like, I do have a comment on what my colleague here said, depending on the regarding the having people from different majors. So actually, I have had the chance to work with different majors before, and believe me, this is like a good thing to do. Like having people from different majors working on something that would. You did not like the chemistry itself. Yeah, okay. So you do have your job to work with quantum computing, not the chemistry itself. So you had like your friend from a medical major, so she's able to like provide you with the information you need to do whatever. Yeah, and that's what you did. Like actually did a great. I liked you a lot. You are like one of the best teams I have seen today. So yeah. So yeah, it is actually a good idea to have people from different majors working together on something that would actually need them all working together. So that's all my only comments. I had just on what she said.
Totally agree.
I see. Yeah, okay, but actually also looking that this is actually a competition and all of the teams had the same time. So yeah, it's not a matter of time. You all have the same time. It didn't like you didn't. It was like biased or something. You all had the. I'm not aware of what happened before. I'm not aware of what happened this time, because I do not have any information about what is going on here. I just came with my friend, honestly, but I don't think that this was biased at all. All of you had that. Yeah, actually, yeah, I see. Yeah, so it's like a matter of fun that you have like small. Actually, working under stress and working under this stress is what makes it like fun. Yeah.
You will have more time in July actually, but let me ask you something actually. What you will learn actually after this mini hackathon? What you will try to learn? First, you are here. You enter the hackathon, right? Okay. What you will do after this? Exactly. Okay.
There's different courses and enter to Udemy and Coursera, and I found very interesting courses and very nice and very yeah, beginner for the beginner, and I'm interested in it very much. But still, I need more time.
Agree.
I need more time.
Yes, of course, like, but listen to what you mentioned now. Actually, you already started learning. Actually, this is
Yes.
one of the main objective of the hackathon.
I am associate professor. I can't represent anything that I don't understand 100%. At least for me. Yeah. For that, I need more time to be. Yes.
You have 2 months till the next mini hackathon.
We'll see. Sorry, I talk too much.
No, it's okay.
I have another opinion beside my friend. My impression, even though we went through a hard time and we did a hard work, but actually when I see the amount of results and the amount of effort we do this one day, comparing to other days or other weeks,
Normal days.
the person feel that he is excited to do something and
Achievement.
yeah.
Sense of
So,
achievement.
because like last week I was disappointed a little bit, and I I wanted to, I didn't want to participate, and I didn't know how I can achieve this result with my friends. But alhamdulillah, we did a good work. So my impression is very good about this hackathon, and I hope we did better next hackathon.
You already did very good job, by the way. Okay.
We were in the turbo mode.
Turbo mode, yes. Super turbo mode.
Super
exactly.
turbo mode, yes.
Okay. Any feedback? Okay, great. Okay. So we'll just wait for final results. Stay tuned.
بسم الله الرحمن الرحيم. Alhamdulillah. Again, thank you everyone, and thank you to our speakers. Thank you to Engineer Samah. He has been sharing throughout the day. It's very helpful, and of course for the open discussion, he also shared. And thank you to everyone who organized, to the mentors, and to all of you for participating and facing up to the challenge. And it's now time to announce the results. Again, excellent presentations, everyone. And we have the results, and they're very close actually. So everyone again is a winner. You faced up to the challenge. You built something useful in a very short time. Stressful, I know, but it pays off. So the results that we have are as follows. We have in third place. Anyway, in third place we have Team ETA. Congratulations. And in second place, we have Team Alpha. Congratulations. And in first place, we have Team Beta. Congratulations. That day was wonderful, very efficient, and very fruitful. Thank you all. It's really a pleasure to have you here at the Library of Alexandria. And we look forward to seeing you again online and also in person, inshallah, in September, inshallah. Engineer Sarah.
Thank you very much.